Right. So please follow properly so that you can quickly grasp what I'm trying to do here, because almost everything here we have covered in the past. It's just a matter of revising them and connecting together. Okay. So now it's pretty easy to see the two partial fractions, right? Partial fractions are actually created based on the denominator polynomial and the eigenvalues of that polynomial, the poles or the roots of the denominator polynomial or characteristic equation. So the first one is some number a over 1 minus 3z minus 1. The other one is b, some number over 1 plus 2z minus 1. This b is nothing to do with the previous b, capital B, right? That we have discussed. All right. Now the next step is how to calculate a and b, and for that we use partial fraction. The cover-up method. So this is the cover-up method in action. Right? To calculate a, what you need to do is get your entire expression hz, multiply with that single pole denominator, right? That is 1 minus 3z minus 1, which is in fact this one, the first one. Now we are referring to the first one, and we know hz, which is this one, right? And then evaluate the whole expression at that pole, So what is the pole here? 1 minus 3z minus 1 is equal to 0, right? Then you can calculate what is z to the minus 1. You're trying to eliminate or remove z at that pole value. So it is obvious you z minus 1 or z or whatever, it doesn't matter. Of course, now we have z minus powers, right? So therefore, we'll use z minus 1 instead of z, okay? So z minus 1 is actually 1 over 3. It's clear, right? So 1 over 3 z minus 1. So when you substitute that value for every z here, right? Every z means z minus 1. You get a equals 2 over 5. Please follow what is on the screen. And check whether you have understood everything, right? If necessary, you can write it down on your paper and work it out yourself. Then you can quickly revise your memory on this. You may have done this before, right? So it's just a matter of refreshing that experience. Now, to calculate the second coefficient, same process, but you apply it with not 1 minus 3z minus 1, but 1 plus 2z minus 1, right? Because this is the second term. 1 plus 2z minus 1. So what you need to do is to multiply this term hz with this one and substitute for z minus 1 minus half, okay? Because when you set this to 0, z minus 1 is minus half. So there you can see z minus 1 is equal to minus half. You put it over here, right? Your result is this 3 over 5. Now we have the two coefficients, right? The first term 2 over 5, the second one is 3 over 5. Now you can write it like this. Okay, the rational polynomial, now you have broken into two partial fractions. They are both first order and very familiar terms in the zTransform table. right? So I think we are in a better position to do the inverse transformation now. Now, if I recall from the Z transfer table, I want you to think about this one, right? When xn is alpha n un, right? Alpha n un, this is unit step signal sampled, okay? Sampled unit step. So anyway, so it is a sequence of pulses, impulses, and every impulse is one. Height is one, okay? Height is one. And there's so many of them, right? At regular intervals from time 0 to infinity. But the actual magnitude is alpha to the n, or a to the n, some constant times to the n, right? If your function is like that, in the z domain, the z transform of that one is 1 over 1 minus alpha z minus 1. Remember this format. If you go to the table, you will see this. If the xn is alpha to the n un. Okay, so let me bring you back and to the table. Right. So this one, b to the n. Right, b to the some constant to the power n. The z transform is z over z minus b. Or if you divide every term here with z minus 1, right, you will see this one becoming 1. This is 1 over 1 minus b z minus 1, right? It's the same thing, right? So this one is equal to what? 1 over 1 minus this constant b, then z minus 1, right? So either this or that. This or that. So more often than not, we write the z transform this way. We prefer to have z minus 1 than z. Okay. But mathematically speaking, there's no difference at all. So when you see this format as one of the partial fractions, you are very happy because you know that the inverse is b to the n, time domain. Right? So here we have alpha in this particular example, right? Alpha. So let's take the first one, 2 over 5. That's a constant anyway. You can just keep it over here. And after that, it is 1 over 1 minus 3 z minus 1. So that's what you have, right? 1 over 1 minus 3 z minus 1. So therefore, the inverse z transform of that one is this quantity, right, to the power n. This quantity is actually 3 to the n. Un is anyway there. This is the presence. It represents the presence of the pulse, okay, impulse at that point. Un. Similarly, the second term is 3 over 5, constant times this term here. Right? This is actually minus in the partial fraction expansion. So, and also in the Laplace table, it's always minus. But if you have plus, you can break this into two minuses. One, you just keep it over here. The other minus comes here in front of 2. It is not just 2, it is minus 2. So, minus 2 to the power n. Okay, un. Now, this is your solution. Inverse z transform of that z transform. Now, if you substitute n equals 0, right, you can work out that sample. right? Now from here, right, if n equals 0, that is the first sample, right? You can see this is 2 over 5, right? 2 over 5, 3 to the 0, right? I just drop u to the n, right? un, because it's always 1. Then plus 3 over 5 minus 2 to the 0. So this is minus 2 to the 0. So this is the first term actually, x0, right? In fact, this is not x, n, h rather. So to be precise, it is h0, right? h0, the first term, which is equal to 2 over 5 plus 3 over 5. So you work it that out, right? Find out what it is. So this is how you calculate the first sample. What about the second sample? N equals 1. N equals 1. So it is h1 is equal to 2 over 5. And now you have 3 to the 1, right? Times 3 plus 3 over 5 times minus 2. Work that out, right? So the function is now a function of time. So when you, not time actually, the sample index of time, right? That is n. n0, n1, n2, n3, and so on. You can calculate all of the samples. Now, are you getting a feel about how to use zTransforms, right? And then how to bring it back to the time domain, how to calculate the sample sequence. So this is the whole purpose of taking this time out of the normal theory, right? To study about zTransforms. Any questions so far? I think I gave you a couple of homeworks last time. So can you raise your hands, those who have done those homeworks? These forward zTransforms. How many of you have done it? Please raise your hands. Nobody has done? My God. So nobody has done even a single one? Forward zTransforms? This is unbelievable. I have to tell you guys, this is not a joke, right? So you're supposed to spend a little time more than this lecture time, right? When you are given a little homework, right? Spend half an hour. Find that time, right? To work that out because it's extremely important. Otherwise, you are fresh. Every week you are going to a lecture afresh. And background is, if you have already done this kind of thing, that's fine, right? You don't have to do my homework, right? But if you have forgotten these zTransforms and all these things, you better spend some time to do that. Today also I'm going to give you certain things, and if you're not coming with some practice, and at the end you find it very difficult to follow, right? So because I'm not going to work out with you a lot of tutorials, lot of past papers. We don't do that now, right? We teach you and we work out few examples, right, during the class, and give you little homework to do, right? Because we are not asking you to work out so many questions, right? and taking you by hand all this long, right? Like in O-level and A-level. So you're now a graduate student, so you're supposed to behave responsibly. So working out the homework is extremely important, right? It is a preparation for the following class. So there's some activity in the chat. I uploaded the slides, didn't I? Oh, video, I upload the video. Didn't I
I think,
upload this
sir,
one?
nothing was uploaded, sir, when last time I checked.
Let me show you this one. Wait. I think you can see my screen, right?
So we can see this.
Yes. So it's a bit slower, but anyway. So this is this one, right? Your course, digital control system. It's not there. They actually uploaded. What happened? I uploaded. I'm pretty sure I uploaded it. I renamed one of these slides this week's also. Something has happened. I don't know what. Anyway, I'll upload it today again, right? Sorry about that.
Thank you, sir.
Okay. Back to the slides. Right. So then today, after the lecture, maybe you will be able to do that homework and also the inverse and together. So anyway, if you want to get rid of this zTransform thing, which is actually a tough thing for many people, right? Okay. There's another one. Find the inverse zTransform of the following exit zTransform. Can you give it a try? Take a few minutes. This is x z I'm giving you, and can you break this into partial fractions and then calculate the inverse transform and then find out the time samples, okay, of xz. Eventually, can you calculate me x0, the first sample, x1, and so on? It's terrible. Right. So give it a try to calculate. Sorry, it's not working. It's probably my optical mouse problem. Right. But I think you understood what you're supposed to do. Try to work out x0, that's the first sample, x1, the second sample, x2, the third sample. Out of this, right? X is it. You're supposed to break this down into two partial fractions and then get the inverse z transform. Then you are in time domain, n, right? Substitute n equals 0, n equals 1, and so on. Right? Take few minutes. Okay, so let me show you the answer. So this is the first step. We break down into two fractions, 0.75 as the first pole, and the second one is minus 0.5 second pole. Okay. And also this is m greater than n case. So there is no constant term, right, in addition to the partial fractions. Now, both of these terms, right? Now here you can see it is z over this whole thing, right? So technique we often practice is that you bring this z to the left hand side, right? Get rid of this z on the right hand side, right? So that it becomes like this. It's a bit easier to handle, So if you look at the whole thing, right, it is z to the minus 1, this thing. But you can actually work out this as z to the plus powers, right? So what do you do to do that? To multiply the whole thing, right, top and bottom, right, with z square, and this is also multiplied with z square, right, z square, both numerator and denominator. When you do that, you get z to the positive powers, right, in your rational polynomial. So depending on how easy it is to work with z to the minus powers or plus powers, right, depending on that, you can do this change or reformatting the rational polynomial into z to the positive powers or z to the negative powers, right? So in this particular case, during the time of figuring out the partial fractions, a lot of people are familiar with working set to the positive powers. Pretty sure, right? This is how we have done in your A level, right? So that's why this positive powers here, right? You can see it over here, positive powers. And depending on the requirement, we can go back to negative powers of z at any time, no problems. Right, so we figured out the first term C1 over Z minus this, and second term C2 over Z plus 0.5. And we do the partial fractions. The first one, C1, is like this. When the pole is 0.75, and the answer is 4 over 5. To calculate C2, the second coefficient, the pole value is minus half. And this is the whole expression. The answer is minus 405. So with C1 and C2, right, you can write down xz over z. Remember, we have taken one of these z's to the left-hand side, okay, to help us in the partial fractioning case. Because in the partial fractioning, the numerator is better to have your numerator is constant. Now, with the two partial fractions worked out, now you can bring back this z to the right-hand side where it came from. Right, and then it goes here and here, it becomes 4, 5, z over z minus 0.75 minus 4 over 5 z over z plus 0.5. Now we know pretty clearly these terms are familiar entries in the z world, right? Z over z plus 0.5, z over z minus 0.75. Anyway, it is something z over z minus a certain quantity. And we know that in the time domain, it is this quantity, whatever it is, with the negative sign here, to the power n. So this one will produce 0.75 to the n, and this term will produce 0.5 to the n. okay, in time domain. So as it is given here, the first term is 4/5 times 0.75 to the n. And the second term is 4/5 negative and 0.5 negative. Okay, this one 0.5 negative to the n. So when you combine the two sequences together, this is the result. 4/5 is common. It is 0.75 to the n minus 0.5 to the n. So you can calculate the first sample when you substitute n0. The second sample when you substitute n equals 1, and so on. Now, could you please raise your hands, those who have done it properly, who have got to the final expression with n say x0, x1, x2, and so on. Oh, we have one person. Good. Very good. Anybody else? Only one person. Anyway, those who have got through half mark, say those who have completed up to the partial fractions, those who have figured out the two partial fractions, please raise your hands. We have 5 people. Good, good. It's counting. We have 6 people, 7, 8, 9. Right. Now we have a pretty good idea about where the problem is. Problem is you don't have any major issue identifying partial fractions, but the problem is how to get from there to the inverse zTransforms, right? So it is just one step. It is not a complicated process, right? Just one step. What is that? It is how to get from here, right? How to get from here through this step to this one, right? Just one single step. I think it's important that you understand how to bring it from here, right, to here. So watch very carefully. I think you can figure that out. You need the zTransform table entry, which says if you see something like this, say z over z minus something, this one. This is the format. This is the format you need to remember. Z over z minus something. Right? And in this case, first case, it is 0.75. In the second case, it is minus 0.5. And then you raise that to the power n over here and here. Okay, so remember that. All right. Now, let us also work out a little example on repeating poles case, right? So again, through an example, find the discrete time sequence xn with the following zTransform. So you are given the zTransform of the solution, but we don't know what it is. We have to bring it back to the time domain. And then this is the process we follow. We figure out that there is a multiple pole here, repeating pole at z minus 1, okay? Pole at 1 is repeating twice. So when we break down this into partial fractions, it's slightly different than what we have done already, right? This is case 3, actually. So how do you do that? This is how we write when there is a repeating pole. C over Z minus 0.5. This is the first one, right? First pole is 0.5. The repeating pole is at 1 and repeating twice. So you have to write down this one, D1 over Z minus 1, as the usual case, right? Non-repeating poles. And then there's another one, D2 over Z minus 1 whole thing square. So this is the new thing, right? Not actually new, but assuming you have forgotten this, the way of writing the partial fractions. So if it repeats 3 times, then you need to write another one, D3 over Z minus 1 to the power 3. Okay. All of these terms up to the highest order, you have to write. Then you have to calculate 3 terms, C, D1 and D2. See, you calculate using the previous method, cover-up method, pretty standard stuff, with Z equals 0.5, okay? And the answer is 2. I'm not going to work it out again because we have done it already. But for D1 and D2, we use a different formula, this one, which is already given, but you need to digest this equation if we can use it, right? It comes like this format, 1 over m minus I factorial d m minus 1 over dz m minus 1 is the differentiation of this term z minus pk to the m xz. It looks a bit long, a bit scary. So that's how things that are not simplified anymore looks like, right? So therefore nothing to worry too much about it. Just follow it. Now we know this m is 2 because the pole is repeating twice, so m equals 2. I is a variable, right? I goes from 1 to 2 here. If it is multiplicity 2 case, I goes from 1 to 2, right? Two values D1 and D2, right? You can see it over here. So let's calculate D1. So I equals 1, right? Set I equals 1. So this is D1. There you can see m is 2, 2 minus 1 is 1, 1 factorial is anyway 1. So 1 over 1 is 1. So there's nothing coming from the factorial here. Then you have d, 2 minus 1, which is 1, over dz, 2 minus 1. So again, this is first derivative, d over dz. And then within the bracket, you have z minus pk, right, which is z minus 1, this one, right, to the power 2. You can see it over here. Then xz. Now, in this particular case, our xz is this whole thing on the left-hand side. It is xz over z, whatever function. This z you don't see here in the theory. The theory says whatever you have on the left-hand side. So this is being xz, and so is this one, xz is just a coincidence. They're not the same. This says, as you know, your transfer function. And it is xz over z in this particular case. So you have to get this whole thing, xz over z on the left-hand side. And then substitute z equals pk, the pole value. In this case, it is 1. So z equals 1. We have not done anything differently. We just followed what the theory says. Again, I'm not going to give any proof or anything here because this is pretty much mathematics, right? You should have covered. So then once you simplify this one, this z minus 1 whole thing square, xz over z, it is this one, is already given, right? So this is the given transfer function. If I pedal back, this one, this whole thing, right, Without one of these z comes over here, the other z remains there. All right, so z over these two terms in the denominator. So then you have to simplify this one. Z minus 1 cancels out, right? And z over z minus 0.5. Now you do the differentiation as a ratio, right? V du minus u dv over v square. Remember how to differentiate a ratio, u over v, right? And you get to this one, simplified version, and then you substitute z equals 1, you get to 2. So once you get this, you can go through it again. Make sure you do that and cover up this basic knowledge. Okay, then you will feel kind of confident, right? Because this mathematics is not that difficult. It's kind of easy, but there's a fair amount of length. You have to work out, you have to write. That's a bit of a pain, right? But you might enjoy with the feeling that you are actually able to handle this kind of things, right? Right, so we have found D1. Now it's time to find out D2, which is D1. Substitute I equals 2. So then this becomes 2 minus 2, 0 factorial is again 1, right? And this is 2 minus 2, 0. So in that case, there's no differentiation, okay? Z minus pk to the 2, still there, x is z. So that part remains unchanged. Right, so D2 looks like this. Okay, so there's no differentiation. It's just the first term over here. Right, z minus pk to the 2. Then x is z. So z minus 1 this time to the power 2 and x is z over z. So once you substitute, you get to this one. Answer is 2. Now you have found D1, D2, and C. You can write it down as 3 partial fractions. Now, each one you can directly transform back to time domain, because this is, as you know, z which was here, you have to send it back over to the right hand side, right? Z over z minus 0.5 is 0.5 to the n, like this. And z over z minus 1 is just 1. Okay, you can write if you want, like you wrote here 0.5 to the n, you can say this is 1 to the n. 1 to the n is anyway 1. Why you write it? So then this one is z over z minus 1 whole thing square. This is new in the sense that is within the lecture, we have not encountered this one. So you have to look at the zTransform table. What is it? What is this one? Especially with this square thing. This one is fine, right? Z over z minus 1, this one, and this one. We have seen these things earlier, so there's no problem with this one. But what is this? Z over z minus 1 whole thing square. So we have to figure out something like this. Z over z minus a or something, right? The whole thing square. So shall we go back to the table? Can you see something? Can someone tell me what row should I look at?
6 constant. 6.
6, number 6, correct. So if you look at number 6, this one, Let's see it over here. Number 6. So if you see z over z minus 1 whole thing square, the answer is n. The answer is n. Okay. So what about this one? Number 8. What's the difference? Difference is with the b, right? So you can see it is bz over z minus b whole thing square, right? B is just a constant. You can bring it forward over here. It doesn't matter, right? So when you see z to the z minus constant raised to the power 2, right? It is that number which is over here, right? Raised to the power n in the time domain. Okay. So let us go back to where we came from. Right. So the third term, right, z over z minus 1 whole thing square, right? Straight away, it is 2 to the n, this one. Okay, you figured it out. But if it was like z minus something else, not 1, right? Maybe 0.5 or is it plus half or is it minus 2 or whatever, make sure you take this number and raise it to the power n. Okay, raise it to the power n, and make sure you also do this little adjustment here, right? So if it is say z minus 2, for example, then there should be 2 over here. Okay, if it is z minus 3 whole thing square, then there should be 3 over here. If you don't have 3, adjust it over here. Okay, by dividing by 3 over here. You put 3 over here and 3 over numerator, denominator. Then you are fine. Then it is 3 to the n over 3n. Okay, fine. So now this is your time domain. 2 times 0.5 to the n minus 2 plus 2n. So you can see n is in the main line, and also n comes over here as the exponent. So if you want to simplify, you can write it this way also, 2 times, because these are common, 2 times n minus 1 plus 0.5 to the n. So substitute n equals 0, 1, 2, 3, 4, and calculate the first few samples and draw it. Okay, please do that as a homework, then you will see it is complete. All right, so let's take a little break over here, but 5 to 10 minutes, and I'll see you after the break. Any questions before we break out? Any questions, please, about the example we just completed? Right, fine. So let's break for some 5 to 10 minutes. All right, welcome back. So I think I want to believe that everyone is comfortable with zTransforms, right? If you are not comfortable with zTransforms, what can I say? It's a bit of problem going forward, right? Every time you see this Z letter, right? You don't like it, no? You don't want to see this Z letter if you don't understand what it is, if you are not comfortable with it. So that is why it's extremely important that you um, revise yourself with the basic zTransforms, right? Spend some time. And I'm sorry that documents I uploaded are not there. I don't know whether there was a disconnection during the upload and all that. But according to my best memory, I saw it uploaded, right? And now it's not there. Not only the slides, video and everything I uploaded. A video in a few sections, part 1, 2, and 3, I remember. Because there were many power interruptions, disconnections during the lecture last time. Okay, so to help you consolidate your knowledge about zTransforms and to build your confidence, there's another one here, example, right? What is it? There's a zTransform, 1 minus e to the minus at times z over z minus 1, and z minus e to the minus at. That's what you have, right? And you can assume this as a solution that you synthesize in the Z domain. Now we want to bring it back to time domain, right? So what we do is we bring this Z to the left-hand side and make it Fz over Z. And this is a general practice. Now you know why we do that, because we later will send this to the right-hand side after partial fraction expansion, okay? So then you can break this down into the two partial fractions. This is another skill you need to develop. A lot of people have done a lot of mathematics of this nature, how to break the rational polynomial into partial fractions. There also you need a bit of practice. So then here there's no need to do any using the cover-up method or anything to calculate C1, C2, and so on, because we directly write it, the two partial fractions, right? If you just follow the theory, you would have written C1 over this and C2 over this and all, right? But don't be so mechanized, so automated, right? This is a simple thing. You don't have to calculate C1 and C2, the coefficients. Straight away, you can write this one. Okay? All right. And then you bring this Z that you have brought to the left-hand side back to the right-hand side, right? So Z over Z minus 1, Z over Z minus e to the minus at. Now, this e to the minus at thing, right, is a number, isn't it? It's a number. You look at it. If you figure that out as some exponent, you are wrong. If you look at e is a number, a is a number, t is a number. So e to the minus at is just a number. So treat it as a number, just like 1 over here. Okay. It's not any exponential thing, right? So now in the table, you can see Z over Z minus 1. This is the Z transform of delta function. Delta means just 1, okay? Sorry, the unit unit sample, UN. This is UN. So in the time domain, it is just unit step 1, right? So it is this one. You can see this long one here. 1, 1, 1, 1, 1. All the terms are ones, right? Starting from here. This one is kind of missing. There should be 1 over here, right? This should be arrow here also. So that is this term. And then the second one, again from the Z transform table, you can see Z over Z minus a constant. z over z minus a constant. This is z over z minus 1, which is also a constant. But this constant and this constant, when they are different, their z transform is going to be a little different, right? This is actually 1. This is actually this constant, whatever it is, e to the minus 80, this whole thing, right, to the power k. K is the time index. Now here you can see it's k. This t, you may drop this t. It's okay to not to write this t, but k is important. K is the sequence position, right? 0, 1, 2, and so on. And you put it over there. Together with this one, you raise this quantity to the power k. So in my early examples, right, you have done it, this n is the time index, right? Raise it to the power n. Now you can see it over here, z minus 1, right? This is this one, z minus 0.5. So you raise this to 0.5 to the n. Very same thing, but I'm sorry about this index being k here. Sometimes I use k as the time index, sometimes n as the time index. So this can cause problems. So I'm sorry about that, but I think you can figure that out. So then this term is an exponential decay because of this negative sign, e to the at k. K is 0, 1, 2, 3, 4, and so on, and it's negative. So it's coming like that. These ones, these samples, right? These are the negative samples. Negative. This is positive, negative. You can see these negative numbers, right? So what remains is the difference. This is plus, this is minus. So the response is this much at t, this much as 2t, this much as 3t, and so on. And at 0, the value is 0. This minus this is 0. The first sample is 0. So when you draw the difference between these two, you will get it like that. First sample is 0, then you get improving amplitude, height, and eventually it becomes 1 exponentially. Okay, so it's a first order rise. It's a first order rise. So what is required here in terms of skill is that when you are given this kind of thing, you should be able to figure that out. Okay, I want to get this Z to the left-hand side and then break this into 2 partial fractions and then inverse zTransform and then to figure out the time samples. Okay, that is the skill required. One more thing I want to let you know is that how do you write this mathematically, right? This is one way of writing a sample sequence mathematically. You can see it's a summation. As you understand that summation from k equals 0 to infinity, k is the time index. I would have stick to n rather than k. Anyway, so then the first one is this one, the second one is here, third one is here. How do I write all these things mathematically? So let's say I know the values of these heights, right, as fk. So I can write the sample height as fk, right? Fk is the sample height for a given k, right? It comes from here, You just put it over here, okay? And then the position. How do I specify the position mathematically? Using a delta function, delta t minus the position, kt. When you do that, this function is everywhere 0. It's a continuous function, 0 everywhere. And at that point, it's 1. And then again, it's 0. It's like that. So as you change k, it again moves from 0 to that point, and then 1, and then 0. So similarly, for all these positions, kt, k from 0 to infinity, you have these delta functions. So this is a delta function which is continuous. Continuous function, 0 and then 1 and then 0. Again 0 and then 1 and 0, like that for every k. you position this unit impulse, and then you multiply it with that particular height of the sample at that point, and then add them together. So this becomes a continuous function with zeros in between. Between samples, it's 0. Okay. So just remember that, how you use the delta function with delayed delta function, and sample sequence, how to write discrete sequence as a continuous sequence, right? Okay, now the next thing is properties. Again, nothing new here in terms of the analogy. At least every transform has forward, inverse, and the properties, right? Basic transforms and properties. Properties help us to handle complex problems, and it shows you how you can assemble the basic transforms together, right, and apply to a maybe bigger complex problems. One property is linearity, so which means if you have two sequences, x1 and x2, right, you can actually calculate the z transform without any problem. But if you have these two sequences multiplied by two different constants and then add them together, what is the z transform of the resultant sequence, right? So don't have to go back and work it out from first principles, but instead, if you have already calculated x1 and x2, they are z transforms like x1 z and x2 z. You can combine them as shown here, multiply with the constants a and b and add them together, right? So this is what is called the linear property of z transforms. And when you do that, remember I was talking to you about region of convergence, right? And the region of convergence of the resultant sequence, this one in z domain, is Rx union or intersection Ry. So you calculate your z transform, this one, right? Z transform region of convergence, that is Rx, and the region of convergence of this one, Ry, and the common area between the two, right? So it's not defined elsewhere, right? Shifting property. If you shift a sequence, right, like that, your sequence is xn, and you shift it, now it becomes n minus k, right? N minus k. So which means you have shifted to the right by k steps. Shifted to the right by k steps, right? It's a new sequence. And if you think, okay, I have to work out the z transform from first principles, you're wrong. You don't have to do that. You can get the z transform of the unshifted sequence, right? Without any shift, you have already worked it out. So just put in front of that z to the minus k. That's all what you need to do, right? Example, if you have xn minus 2, which is a sequence xn shifted to the right by 2 steps, shifted to the right by 2 steps, which means x0 is now appearing at x2, right? Shifted to the right by 2 steps. So when you do that, how the z transform of that change, right? That's the question. So you get the z transform of the unshifted sequence, which is xz, and put in front of that z minus 2. Z minus 2. That's all. So let me show you a bit more mathematics about the shifting here, right? To build your confidence. Now, this is our sequence. Let's say yk minus L. All right. Again, I'm sorry about changing this sequence indexes, right? Indices rather. So k minus L. K is the time index, right? Which is from 0, 1, 2, and so on. L is the shift, shifted to the right by L steps, right? So what is the Z transform of any sequence, which is summation from 0 to infinity of the time index, which is k here, and you write down the expression that is yk minus L, and then put z to the minus k. This is by definition. You can write it anytime for any sequence. What is the C transform? Just this. Get the summation z to the minus k, k from 0 to infinity, the function itself. That's it. Now, what we do next is that Z transforms, we don't like it to be like this, yk minus L. We don't like it, right? We would like to have one here, k or L or whatever, with z minus the same thing, right? Because that is in line with the basic C transform definition. So therefore, what we do is we gonna replace this k minus L with another variable, time variable. Let's call it I. Right? When I take this k minus L, which is equal to I can write yi. I like it that way because that is in line with the definition. So when I do that, I have to look around what is happening around. There's a summation which has a lower limit and upper limit. I have to change the limits also, right? With this introduction of I, because now k is not anymore the time index, it's going to be I. So summation limits also to be changed accordingly. Right. So the summation limit 1, which is k equals 0. So as k goes to 0, I goes to L minus L. That is the lower limit corresponding to I, right? Or corresponding to k equals 0. And on the other end, as k goes to infinity, this one, I goes to infinity as well. Because infinity minus L means again infinity, right? So these are the new limits for I, corresponding new limits, right, for I. So now I can write this one as summation I from minus L to, right, so minus L to infinity, fine, yi z minus k. Now there's no k anymore. I have to replace k with I plus L. Okay, so it is minus k. If you want to write like minus k straight away, take k to the left hand side, minus k, and I to the right hand side, minus I. So it is minus I minus L, this one. Okay. So now we know that we deal with only partial systems, which means summation from minus time index we don't consider. Right, so I from minus L to 0 is anyway 0. We don't have any y in that region. So it is basically the positive part, I equals 0 to infinity, yi z I minus I, z minus L. So you break this into two terms. I is the variable time index and L is a constant. So you can take z to the minus L in front of this, right? And then what remains here is the definition of C transform. I equals 0 to infinity, from 0 to infinity, yi is equal to the minus I. So this is the definition of Z transform. You can say y is it. In front of that z to the minus A. Okay, right. So that's the definition of the shifting theory. And this is the shifted sequence, yk unshifted. This is k minus l shifted. So you shift it to the right by l steps. And there are other properties also. I'm not going to take you through all of these properties again. It's not a standard zTransform course. Just want to revise you their time reversal also. If the n is minus n, right, which means it's not going from left to right, but from right to left, reversal, then zTransform will change this way, z to the minus 1, right? All the z's will take the form of z minus 1. Take z out and put z minus 1 there. It's not multiplying with z to the minus something, right? It's changing z to the minus 1, just that. When you do that, your region of convergence will also change like that. It will be inverted, okay, or rather reciprocal. Multiplication by an exponential, if it is like this, there is a time sequence, xn, and then all of a sudden you get a to the n. Time exponent is a constant raised to the time index, power of time index. So you don't have to calculate the zTransform all over again. If you already have calculated the zTransform before this modification, right? Use that and replace the z, all of the z's, with alpha minus 1 z, just that. Okay, right. And there's another theorem, convolution theorem. Again, this is a very, very important theorem. I think I explained this to you in depth in the first semester with continuous time, right? And it is happening here again in the discrete time. Yn is equal to xn, convolution hn. You can see the two things, right? Xn, hn. When you look at this, what should come to your mind is a signal and a system, right? Let's say this is your system, this is your signal. Signal goes into the system, and then something comes out of the system, that is Yn. So what's happening in between from input to the output is that input is convoluting with the system interaction and produce this output. Now, the beauty of this one is that convolution is mathematically very complicated, right? But if you look at the same thing process in the Z world, it is very, very simple. You have the zTransform of the signal. Also, you have the zTransform of the system, right? So they are just simply multiplying each other. That's it. Multiplying each other. So this complicated operation between the input and system, right, is formulated using this transform as a product in the Z domain. That's why these products are very important. Somebody had figured out this whole thing and introduced this transform so that when you multiply the transforms, you get the product in the time domain, in the convolution integral, right? Right. So actually, we should be thankful to those great minds who have seen through all this complicated interaction between signals and systems, entirely mathematical, right? And formulated these transforms. Now, let me shed some light into the process because I feel if you can see things, you will be able to understand the meanings of this mathematics, right? Which is not actually visible otherwise. So I have two signals. So I would say one is a signal, the other one is the system. So these are interacting, right? These are interacting. F1 is it, F2 is it. So this is how we write the convolution sum, right? The first sequence, discrete sequence, f1 kt asterisk f2 kt, right? This is the convolution. The mathematical description for convolution is this one, summation. Now here I have n as my time index, n equals 0 to k. K is the present time here, right? I am at this time right now, my present time, kt. F1 nt times F2 k minus nt. So this is the zTransform, convolution sum defined, right? So what is it? Let's look at the physics behind this, right? Not mathematics. So I'm here. This is my present time, right? This is my present time. So before this time, right? So there's a signal. This is a signal at this moment. This is the signal 1 step ago. This is the signal 2 steps ago. This is the signal 3 steps ago. Like that. This is the signal history. You can see it here. When you go too far back in time, you can see the signals, but there is no effect, any residual effect of these signals at this time, present time, because they're too old. All of the effects have already decayed out. So when I say decayed out, there is a process of decaying, right? And that is described by the second system here. Let's call it a system. What the system does is, it produces an output for every sample, and gradually that outcome or output rather diminishes. It doesn't stay forever. Like say, for example, if you bang on a bell, when you go to the temple or the church, right, you can bang the bell, right? Then you see the ringing going on, very loud noise initially, but gradually it decays out. And after about a minute, there's nothing remaining, right? So if you are away from, say, 1 minute away from your initial bang, right? You don't listen anything from that bang, right? First one, which is older than a minute. So therefore, you must be looking at a certain recent samples contributing to the outcome now at this moment. There's no need to go back beyond that point, right? So that is n. This is that n, which tells you, okay, you have to look back n steps. No point of looking at beyond that. Okay, right. Now, the value of the convolution sum at this moment is calculated this way. You get f1 nt, right? Say n is over here. This is that sample in the past, right? You are here now. This is the sample at nt. Your time is now kt, right? From that point, that is the onset, up to now, what is the time? K minus n, isn't it? K minus n. This is the time, decay time for the sample at nt. This is what we are doing in convolution sum. We figured out a way, a normalized decay function, let's say f2t is that one. For any sample, when you multiply with f2t, you get the value of that sample, right, at this time, present time, kt. How much of that has already been decayed? It's not a linear function, it's a non-linear function sometimes, right? So whatever it is, you have to multiply the value of the sample, initial sample, that is fnt, and multiply with f2 k minus nt. K minus nt is the time elapsed. So that is for fnt. What about n plus 1, this one? There you get even shorter time of decay, right? So all these decays are captured over here. Samples and their decay ratios. Sample and decay. Sample and decay. So like that, you have to add them together for the entire history. entire history. So therefore, we'll start from 0 to k, 0 to k, all the samples. The first sample, it has undergone a longest decay. So F2, right, k minus 0 t. K minus 0 means entire kt, total time from 0 to now, right, for the first sample. Second sample is one short of that, and so on. So add them together, you get your convolution. So it's very important that you know what it is when you hear that convolution sum or convolution integral. So in Z domain, right? So before that, let us write the sample by sample summation. So as I explained to you, the first sample is F10, and it has decayed for time kt, the total time from 0 to k. That's the first sample. The second sample, F1t, F2k minus 1t, right? So that sample has decayed k minus 1 t time, and so on. Now you put this into the summation k from 0 to infinity, and you write it like that, right? All the samples, each sample you get n from 0 to k, f1 nt times f2 kt minus nt, z to the minus k, right? This is the Z transform of the convolution sum. Is that right? This is the convolution sum, and then you put this z to the minus k and get the summation from k0 to infinity. That is the Z transform of the function, any function. And this time, the function is convolution sum, this one. What you have on the left and the right is actually the Z transform definition. Now what? If you look at the two summations here, right? The first one, k from 0 to infinity, you can write it like that as a 2D graph. This is k, this is n, right? K and n. K from 0 to infinity, right? For each k, you have the second integration or summation rather, n from 0 to k. So you go along k-axis from 0 to infinity, and for every k, right, let's say you are here, you have the second summation n from 0 to k, 0 to that k. So it's a 45-degree line here. 45-degree line, and this is the summation. Surface summation, right, or double summation. But if you look at the same area, you can draw it like that also, this way or that way, right? So what is this one? This is you take n from 0 to infinity, n from 0 to infinity. For each n, right, you get the summation from k from n to infinity, n to infinity. That is also right. You can write it this way or that way. Okay, so get the two summations as you have written here, right? K from 0 to infinity, and then n from 0 to that k, whatever you have selected, right? Or you can say you are going to sum from 0 to infinity along n, right? And then for each n, you get the summation from n to infinity in terms of k. So if you write it this way, the summation, the two summations you can write like that. N from 0 to infinity as the first summation. This is number one, is the first summation. And then second summation is k from n to infinity. You figure out any k, right, equals n, and then you start your summation from that point up to infinity. So this is the convolution sum fnt, f2k minus nt, z to the minus k. Now we're going to introduce a new variable because we don't like this k minus n thing. We will substitute m for that. M equals k minus n. So when k goes to infinity, now you can see here, now we are going to replace k, right? We are going to replace k. When you replace k, not only over here, here also you have to replace this k equals n to infinity thing. And new variable we're going to introduce is m, which is equal to k minus n. So then this part will be m. Okay, that is the plan. So when k equals n, as k goes to n, right, m goes to 0. M goes to 0. Can you see that? K goes to n, m goes to 0 because it's n minus n. As k goes to infinity, m goes to infinity as well. So these are the new limits, 0 to infinity for m. So you take the second summation, replace k with m, right? And the limits are 0 and infinity. So that is what you have written here. This one. This whole thing, you write like that. Then you can see this one f nt remains unchanged, and this one f2 k minus nt changes to f2 mt. Is it? And this k also is replaced with what? Minus k means minus m minus n, right? Like that. And separate it out. Now all the n terms together, all the m terms together, like that. And you have the n2 summation 0 to infinity, very nicely separated out. And this one, summation function z to the minus n. And this one, summation m function and z to the minus m. We can clearly identify as two separate zTransforms. This is f1z, this is f2z, right? So that's the proof. When you have the convolution sum, the zTransform is actually the product of the two zTransforms, right? Of the two functions which are convoluting each other. Any questions about that? Any questions, please? All right. So I'm going to give you this one, right? Two sequences. One is xn. This is the signal, right? This is a signal. Let us draw it like this. There's a signal going into a system. Right? The signal is this one, xn. Oops. Sorry about this. Right? So you have this xn as the signal, right? And hn as the system, and you get your outcome, right? Like that, which is right. The system is defined as delta n minus alpha delta n minus 1. So it's like a FIR filter, finite impulse response filter. Okay. So when I say filter, don't confuse it with the normal filters that like low pass, high pass, and so on. filter means there's some sort of frequency distortion, right? So in that very generic meaning, any plant can be considered as a filter. So it's a very generic introduction of the filter term, right? So this is FIR filter, this one, and there's a signal going into that, and we want to find out the sequence which is coming out of the plant. And these are all discrete, you had some output at time 0 and some output at time 1, some output at time 2, and so on. Right, so this is the signal and this is the system. So Yn is the convolution of Xn and Hn. Find the sequence Yn. So we want to find Yn, all right? So how do you do? So the Z transform of this one, now according to the theory, convolution theory, right? When a signal goes to a system, they interact, it is convolution, okay? So the output is the convolution sum. That is the first thing you should be able to figure out. Nobody is coming and telling you, please work out the convolution sum, right? It's up to you to figure that out. When there's a signal which is going into a plant, right? There's nothing other than convolution which is happening there, okay? So you have to implement the convolution here. Then the second thing is you need to know how do I implement the convolution sum of two signals. This is aligned at zTransforms, and there's nobody coming up and telling you, okay, you first transform the signal and the system into the Z world and then multiply. Nobody's telling you the steps, right? It's all up to you to decide. So in the time domain, you can actually calculate the convolution sum using these equations, right? This one, summation. You can do the summation, right? Just before that, this one. There is no Z transform at all. If you know the two sequences and the two passes, you can do the product and sum. This is sum of products format, right? You have the two sequences, draw them just like this. And then get the first one, multiply with the last one, get the second one, multiply with the one before the last one, get the third one, multiply with the one 2 steps away, like that. One sequence goes this way, the other sequence goes that way. You get the convolution sum. Okay, that's how you work it out. But here, you have tested for Z transform application. Okay, so therefore, the previous way without any transforms is not what you are asked to do. So you need to transform Xn and Hn, both of these, to Z world, forward transformation. Okay, and then multiply the Z transforms, the two Z transforms in the Z world, right? You don't do any of these things. Time domain, no, you straight away go to the Z world. And once you multiply the two Z transforms, you get a result and bring it back to time domain. That is what you are asked to do. Okay. Now, what is the Z transform of the first one? Xn. And Xn becomes Xz, right? This one, Xn, becomes Xz. So this is alpha n un. What is the Z transform of alpha n un? Right? Basically alpha n. It is 1 over 1 minus alpha z minus 1. Or in other words, if you want to write it like z, right? It is z over z minus alpha. If you go to the table, you can see that z over z minus alpha. But if you want to write it in negative exponents, right? Z to the minus terms, it is just this. 1 over 1 minus alpha z minus 1. So straight away, line z world. And then you get the second one, hn, and you want to calculate hz. The first one is delta n. The zTransform of delta n is what? Anybody remember that? What is the zTransform of delta n? Anybody remember that? What is the zTransform of delta n?
1.
1. So that's over there, minus alpha delta n minus 1. How do you calculate the zTransform of delta n minus 1? Any answer? Delta n minus 1.
Applying time shift.
Time shift. How many steps?
1.
One step. That's right. Is it a time delay or time advancement?
Time delay.
Time delay. So time delay of 1 step means z minus 1. There you are. Z minus 1. In front of the time unshifted sequence, which is 1. Okay. So it is z minus 1 in front of 1. We don't write 1. And alpha is alpha here. Is there any zTransform of that alpha? No. Why? Why alpha is just alpha over here? Because of one property. What is that property? If you have a time function and you have the zTransform of it, and when you multiply the time function with the constant, what will happen to the zTransform? It will also get multiplied with the same constant. Okay, linearity. So this is minus alpha z to the minus 1. Now you have two zTransforms, xz, hz. So when you have the convolution sum, which is happening in the time domain, what will happen in the z domain? What will happen to these two zTransforms? Any answer, please? Please answer. So the two sequences are multiplying in this format, multiply and add together, convolution sum. It's a complicated mathematical operation. Correspondingly, in the zTransform, in the z world, right, these two zTransforms, F1 and F2, they have two zTransforms, right? What will happen to them? They multiply each other. F1 is it, F2 is it. There's no convolution here in the z domain. It's simple multiplication. So therefore, these two zTransforms get multiplied. Okay. So 1 over 1 minus alpha z minus 1 gets multiplied with 1 minus alpha z minus 1, like that. What will happen then? What is the answer? When you multiply these two together, what is the answer? This is 1 over 1 minus alpha z minus 1. This is 1 minus alpha z minus 1. When you multiply these two together, they cancel off. These two, the answer is 1. Okay, this is a z-transform of the convoluted signal. Now, if you want to bring it back to time domain 1 in the z world, the time domain is delta n, because you know the z-transform of delta n is 1. On the other hand, the inverse z-transform of 1 is delta n. Okay, is that clear to you? This is a simple exercise, but I think it conveyed to you a lot of things. When a signal convoluted with a system, when the interaction between signal and systems, right? The output is calculated this way using z-transforms. But if you have the freedom to work it out the way you want, you can calculate the convolution sum straight away in the time domain, right? Without ever having to deal with C world, C transforms, right? This way, you can do that. So in a lot of computer programs where you need to do the convolution sum, you can just simply code it. It's easier, right? But now that's how the whole world works right now. They don't rely on theories much, particularly in the computer science world, right? They want to put everything into numbers and then using tables and arrays and all, combine them together and produce a result without ever using models of the plants and all, right? They only need the data, input and output data, and the rest of that they can use reinforcement learning, machine learning and all that, right? Model-free systems. But the thing is, they're not mathematically elegant, they're not mathematically tractable, right? And you need a lot of computational power even for a simple problem, right? But I think we need both sides, right? Data-driven systems, because we cannot model a lot of things in the world, right? We have to accept that. But if you model the system to some extent, that will help you to implement a solution, right? Rather quickly and efficiently and accurately, right? Compared with the same effort taken entirely on looking at the data, input-output data, right? So that's where we are. Whether you want to do it this way, is the computer science way of doing it, right, in the modern world, or do it this way, right, which is much more analytical and authentic approach. The other property is derivative. If there is a function in a time domain, right, which is multiplied by a number, another number, right? Sorry, this is not just another number, it's time index, xn in front of that n. It's a very special case, right? As time goes on, it's multiplied by that same time index n. In that case, the z transform will change like that. You differentiate the z transform of xn, right, with respect to z, and in front of that you need to have minus z. Just remember that. And this is the table in of all the properties here: linearity, shift, time reversal, exponential, convolution, everything, right? So this will be another reference for you. You have the two tables now. One is the standard basic zTransforms, and this one is properties. Okay, right. Don't have to remember any of these things, but whenever required, you should be able to pull it out the table and figure out which cell is relevant to your problem at your hand, and then make use of that theorem or basic zTransform, right? So you need to be able to do that, not to remember any of these things. Right. So then is the initial value theorem. I think don't have time today to do that. Yeah. Right. So that's a very important theorem. I think we should do this next time. Right. Any questions so far? Is everything clear to you? Is everybody comfortable with the basic zTransforms, forward, inverse, and all? Can you guys handle a little problem in zTransforms? All right, good. I get some responses in the chat box. I think it's clear to you, and more than that, I expect you to be able to handle it yourself. I'll upload the materials today, tonight, and you will be able to work it out, right? Next week, I'll take about half an hour or 45 minutes max to finish off with zTransforms, okay? Absolutely necessary. That's why I'm taking this time on zTransforms, right? Even though it is supposed to be covered in the previous modules at a lower academic level. But anyway, it doesn't matter. So that's the plan for next week. First 45 or half an hour time we'll spend on zTransforms and finish it off. And then we get going with the rest of the course. All right. Thank you very much for joining in, and I'll see you next week.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.